Welcome to this video. My name is Mark Scythian. The date today is December 14th, 2024. So this video is addressing those of you who are studying climate science. It is always important to do your modeling based on a thermodynamic fundamental rather than anything else, because energy cannot be created or destroyed, but only change in form. So a engineering and physics problem, or perhaps a geophysics problem that you may encounter in your studies, is the following. It is the determination of temperature profile in Earth's ground, accounting for the evolution of surface temperature across one day. This is a very broad paradigm for which many earth science majors, geophysics, climate science, etc. have to tackle. So stay tuned for the rest of this video, and there are some fundamental solution sets to be mindful of. So what we're doing here is we're finding this physical situation that can be viewed as propagation throughout the ground of a thermal wave characterized by an amplitude, angular frequency, a phase, and a wave number, as well as the phase velocity. So we're talking about the propagation of thermal waveforms, and this is an important aspect of understanding the whole climate science paradigm. And again, it's fundamental information, so we have many functions that correlate eventually to what questions are to be asked. So thermal diffusivity and earth ground to evaluate the differential equation satisfying the temperature differentials, and the deduction via the time-dependent temperature field under the form. So you'll see this in any geophysics course, especially when it's with respect to the propagation of thermal waves and Earth surface temperatures. So we're going to cover these step by step, and understanding the amplitudes and the fractional amplitudes are of utmost importance. So we'll start with the solution set here. So we start with thermal diffusivity, and we need to access the epsilon equation correlating to the data in the model for fundamental values. So we can already posit a square meters per second thermal diffusivity with respect to Earth surface wave, thermal wave propagation. And so it is important to use the differential equation and time-dependent temperature field, especially with respect to the heat equation for a one-dimensional system. So you can use the differential equation such that we're using partial derivatives with respect to the tier function set of u of z and u of t. So taking the derivative of both sides with respect to time and space is the predication for realizing the thermal diffusivity. So now if we ignore everything else and focus on the energy transfer, then we have a correct or predictable model that is independent of those realms outside of the mathematics and physics worlds and the chemistry worlds where the actual information, the source information, is identified. So I'll just let that sit here. So each subset solution, fundamental solution, will be posted, and then I'll move on to the next set after erasing. So next we have the time-dependent temperature field and we're assuming permanent regime, we can use the separation of variables technique to find the multifunctions u of z and u of t in the form of theta z to the exponential function taken to the I angular frequency time exponential function as a constant. So then we have the following iteration where k is substituted with the 1/2 power or square root of the I angular frequency divided into the thermal diffusivity, or the epsilon number, so our epsilon value. So combining this with the boundary layer conditions, u of 0 and u of t, we make that equal to the amplitude times the cosine of the product of angular velocity and time. So when you do geothermal modeling, these constants are an established fundamental. However, if you're dealing with avenues of structure that are outside of the scientific realm, then at least you know what's going on without respect to those with specific means to an end. So the facts you can carry, and if this is an elective course or you're trying to get through your homework, you can use this as a guide as well, and be mindful of the k value and its substitute, not necessarily a numeric parameter, but the function or the fundamental. So a lot of times most students are finished with identifying the interrelationships, but then complicating what k is can kind of slow you down. So you can just use that ratio of the I value times the angular frequency divided into the epsilon or thermal diffusivity and find its square root, and then you have that as a default value for k. So next we have the phase velocity. The phase velocity v sub p is the speed at which the phase of the wave propagates. It is given by v sub p, or angular velocity divided by the k value, substituting k as, again, the default. Then we have our phase velocity as such there. Let me go back here. So again, you can use that 2 times the product of the angular velocity times the thermal diffusivity. Let me get this up. Yeah, there. So it doesn't have a complete parentheses on it, but it is subject to the base value and its square root. So next we have the physical phenomena, the profile T of Z and T of T models the propagation of the thermal wave into the ground. The phase velocity v sub p represents the speed at which the temperature oscillations propagate downward or downwards into the ground. So our depth calculations. It's 1/10 of the amplitude is the proportional constant. So that tells one quite a lot about the thermal wave propagation. with respect to constant values. And if you're doing any geomagnetic or magnetospheric modeling, this can come in very valuable. Go back there. So the amplitude divided by 10, so that is just the natural log 10 divided into k is your z1, and then you can take that from a times the exponential function of the negative k z1 exponent made equal to 1/10 the amplitude. So that is what happens in reality. And then you have the natural log 10 over the k value. So the phase opposition, the phase of the temperature variation at depth z is, again, the angular velocity, or the angular frequency in this case, as a product with time. Its difference from the k value and the z base value, because we have 1 and 2. So we need to get the second one, the kz2, in its difference from angular frequency multiplied times time. So this is just the sum of our angular frequency or velocity times time plus pi. So you could see that in respect to a half cycle of the thermal wave. So that's a pi radians value. So solving for z2, we get let me go back there, get z2, or it would be pi divided into the k value. So this part C, the depth calculations, is that the temperature is never below 10 degrees Celsius. So we need to find Z such that the minimum temperature at that depth is 10 degrees Celsius. The minimum temperature occurs when cosine angular frequency time and its difference from the k number times the z value made equal to a constant of -1. So we have the initial temperature, the T sub 0, minus the amplitude times the exponential function taken to the negative k z constant made equal to 10. So solving z, we get our natural log of the initial temperature minus 10 divided by the amplitude as one quantity and then divided into the k value. So of course the numeric calculations for z1, z2, and z require the value of k as a numeric a measured numeric data. So that would be a practical application, but these are the fundamental concept solutions for each subset. And so that ends this, but we can return back just briefly to the original problem, and you can see here that this whole model is about the base thermal diffusion or ability to diffuse, diffusivity of Earth's ground. So this is where the practicality in global cooling, global warming, global constant temperatures, either the albedo or the hothouse effect, finds its function in these paradigms here. And so it takes a little bit of understanding of the partial derivatives and the differential calculus, but then you can come up with a very practical value that reflects reality. Now everything else is outside of science and probably has more to do with economics and politics, but at least you know what's actually going on, and you can actually write the models and publish them. And if people would take these models and make them a little more practical, then probably everybody will realize how these cycles do do obey a consistent pattern that can be modeled, but it's very not linear, and so thus it's very counterintuitive. So I was asked a few questions on these, and I had a student of mine post this problem here, so I thought I would also share it on YouTube. And those people who are studying geophysics or interested in the Earth level thermal propagation and or distributions with respect to diffusion ability or diffusability, you might want to keep an eye on this video. So you can pause it, and it goes like 1, 2, and 3 here. All right, thank you for watching this video, and have a great day.